Hello, everyone. Hello, Japan. Nice to meet you. My name is Jeehwan Kim. I'm an associate professor at MIT. Today, I'd like to discuss about my group's activity, my group's effort to prepare for the next generation electronics. And more specifically, my group members have been working on inventing and developing the way to appeal and stack the single crystalline electronic component in one place. So in other words, we've been working on ultimate heterogeneous integration system for next generation electronics. So today I'd like to discuss about this technology. And before going into the full detail about that, I'd like to briefly discuss about the future of electronics here. So please have a look at this chart. And I try to categorize three different types of important trends for the electronics. First, bendable electronics. Bendable electronics is already in the market. So there is very, crude form of flexible electronics, which is the foldable phone right now at the moment. So it's you can see the the screen in the form of the bending. So you can actually purchase this foldable phone in the market. Also, there have been a lot of effort to make the rollable TV where you can see actually display, you see the screen at this form of the bending bendable state. So this is actually in the market, but still a long way to go because price is really high and we can still bend this kind of a component much more and we can make it lighter. So, but anyways, for this type of electronic component, flexibility really matters. All right. So also one of the most important trend and feature will be bioelectronics, where you can monitor or record the physiological information of the human body by interfacing the electric component with the body. So by interfacing the electric component of the body, you can actually monitor all the health information. Then you can receive this health information. Then you can process this health information. Then you can make some real-time feedback for your body. Also, you can record this your health information and analyze health information into the cloud. So in order for all these things to happen, actually, you really need to make a device that can have an excellent interface with human body. For that sense, obviously, electronic component has to be flexible. At the same time, in order to have the multi-function in small footprint of your body, you really have to have a stackability of the electronic component. In other words, you really need to know how to stack different types of devices in one place so that all this multifunctional device can work for monitoring your health and analyzing your health. Okay. Please have a look at this trend as well. Three-dimensional electronics. All right. So Samsung has been already quite successful on developing three-dimensional stacked, flagship memories. Okay, because the scaling down of the all major electronic component, we are really maxed out for the real estate for the electronic components. So we really have to look into the solution to stack your electronic component three-dimensionally to enhance the integrability of the memory or logic devices. At the same time, for other like display industry, stackability of the RGB also very important. Reason is in order to have the minimum pixel density for the future of the display, you don't really want to have want to organize RGB pixel laterally. You really want to have RGB pixel vertically, so then you can have a RGB display in one place with a very small footprint. At the same time, you really want to have a multi-functionality of your device in one place. To do so, you really want to stack electronic component in one place, so then multifunctional chips can be stacked together, so then you can work as a multifunctional for example, edge computing device. In this specific example, in this specific edge computing device example, you can have the sensors on the top of the chip. Then you can have a memory to store the sensing information, and you want to have the logic device underneath to process the information. To do so seamlessly, you really need to think of the stacking the different devices in one place. So when you are looking at the future of electronics, flexibility, stackability are the most important things that you have to consider. Okay. In that sense, we have to think about what are the right materials for next generation electronics. Again, you really need to think about the stackability and flexibility, like I just mentioned, but at the same time, you also need to consider the performance of your device, and you really need to think about the cost of your device. For this sense, the question is, can you have stackability and flexibility without sacrificing the performance, without sacrificing the cost? That is the most important question that I have today. And I'd like to introduce how we can have all those four at the same time without sacrificing anything. Okay, first of all, let's take a look at the material choices for stackability and flexibility. Okay, let's first look at the organic materials. In other words, polymer electronic component. Okay, these organic electronic materials has excellent stackability because it's soft material. You can stack, and you can deposit this material at very low temperature. Obviously, this soft material is flexible, and price is really low. All right. So for that sense, this organic material can be stackable and flexible. It's perfect. That's why so far all of this, ubiquitous type of electronics, organic electronics has been, regarded as one of the, solutions, one of the most, popular material for that. However, the performance of this organic electronic material is not very good. Obviously, so far this wafer-based single crystalline inorganic material is much better than organic electronic materials in terms of its performance. The performance cannot be compared to the organic materials. However, if you look at this kind of wafer type of single crystalline inorganic materials that we have been using so far in front end of the line, you cannot imagine to have a stackability of this kind of wafer-based single crystalline material because it's simply really, really thick. It's almost half millimeter, so it's hard to imagine to stack this kind of wafer in one place. At the same time, this is not flexible, this is thick. So if you try to bend this, it's going to be easily broken like this. And price obviously high because this is single crystalline material, inorganic, fragile single crystalline material. So not stackable, not flexible. At the same time, price is high, but the performance is absolutely higher. Performance is the best for this single crystalline electronic component. Then, how can we have stackability, flexibility with this single crystalline inorganic materials? So far, only way to stack this kind of single crystalline material is to perform the heteroepitaxy of single crystalline materials in one place, which is a wafer. By having the wafer whose lattice constant is similar to the device layer, then we can perform the heteroepitaxy of this device layer on the wafer, one layer by one layer. So then you can, stack up this kind of, different single crystalline inorganic materials in one place. However, in order to maintain the single crystallinity, in order to maintain the performance, you really need to grow single crystalline films by considering the lattice matching rules among these materials. In order for you to have a heteroepitaxy, all these materials have to have similar lattice constant. This means the material system that you can stack by doing heteroepitaxy is really, really limited, as you can see here. Then, what is the future solution for the material to satisfy all of those? Okay, so So far, there has not been, a perfect solution for it. So what is dream electronic system again? It has to be cheap, flexible, stackable, single crystalline inorganic system. Now, how can we achieve that? One way to do that is we create ultra thin single crystalline inorganic membranes. If we can do that, we can keep the high performance of the material because it's single crystalline inorganic materials. At the same time, you can have flexibility and stackability because of your single crystalline inorganic component is ultra thin. Also, we can find a way to produce this ultra thin single crystalline membrane with a cheaper price. How can you do that? So to address this issue, my group has been formed in the year of 2015 at MIT, and we have been working very hard to provide a solution for it for the last 6 years. Here, I'd like to introduce all of our effort to do so. So to address this issue, my group is composed of 4 different subgroups. Okay, so please have a look at this. Our group has the subgroup that produce the single crystalline freestanding membranes from all possible conventional 3-dimensional materials, such as 3,5 semiconductors, 3-nitrile semiconductors, or complex oxide system, or compound material system. We try to make this material system ultra thin and freestanding out of the wafer. We utilize our special technique to peel the device layer out of the wafer. Then we can do this from various different types of material. Then we can stack them up so that we can satisfy the dream electronic system. Okay. At the same time, we have been working on wafer scale 2-dimensional material system as well. What's so special here? 2D material is ultra thin and flexible. At the same time, this is inorganic materials. But so far, scalability has been an issue for this material. So my group has been working on scaling up this 2D material at the wafer scale. Then we successfully developed a way to stack this kind of 2D material in one place at the wafer scale. So with this material, we try to mix and match different types of inorganic freestanding materials and stack them up into one place to develop the total new function that can revolutionize in current electronics and photonics. So today, due to the time limitation, I would like to focus on our group's effort on this freestanding 3-dimensional membrane and heterogeneous integration of those materials. And also, my group has the AI hardware group, because after stacking these kinds of all different functional materials in one place, we can have we can generate so many different information. We can collect the information, we can generate the information in heterogeneous integrated chip. Then we really want to process the information at the edges by adding this AI hardware on top of this heterogeneous integrated chip. Also, this AI hardware that prepared for my group is flexible and stackable, so that we can make the fully stacked, multifunctional, ubiquitous IoT chips. Okay, so today I'm going to mainly discuss about these 2 activities in my group. Let me move on to the first chapter. So, how can you make conventional 3-dimensional materials flexible and stackable with a cheaper price by maintaining a single crystallinity? Okay, this is a question. For that, my group has invented a way to do so. Okay, so in the year of 2017, we reported way to produce the freestanding single crystalline membranes from almost any source of 3-dimensional materials. The concept is right here. So we invented and announced this new epitaxy technique called remote epitaxy to the world. The method is as following. So we try to grow the single crystalline material whose chemical composition is similar to the wafer, but while we are performing the epitaxy of the same material as the wafer, we try to locate the monolayer graphene on top of the wafer. Why graphene is needed? I'll tell you about this why later. But anyways, we discovered that even if there's a graphene on top of the wafer, if you perform the epitaxy of the same material, then this material still can follow the crystalline lattice of the underlying substrate, even if there is a monolayer graphene. Reason is quite simple. Of course, I can say that because we completely understood why so far. But anyways, the reason is simple. So if there's a graphene in vertical direction, there will be very, very weak van der Waals, field is going to be applied. But at the same time, on the surface of the wafer, semiconductor wafer, there will be quite strong ionic bonding interaction will be applied to the Z direction, because this ionic bonding force supposed to be much stronger than van der Waals force from the carbon in the graphene. This ionic bonding field can be penetrated through the graphene, and this strength can be stronger than the van der Waals interaction of the carbon. If that is the case, whatever you grow on the graphene on the wafer, this material will follow the crystalline information of the underlying substrate, even if there's graphene. That is what we have found. We verified this hypothesis by growing gallium arsenide on graphene on gallium arsenide. By doing so, we are able to grow perfect single crystalline gallium arsenide by following the underlying substrate, even if there's a graphene. Please have a look at this quite crazy TM figures here. So we found that even if there's graphene between the epitaxial layer and the substrate. This epitaxial layer still follows the crystalline information of the substrate in the remote distance. So we name this scientific phenomena as remote epitaxy. Okay, so that's what we have found. Then why bother you put the graphene between the epi layer and the substrate? Here's the reason. Because graphene provides very, very weak interface between the device layer, epi layer, and the substrate. So once you grow any single cell materials on it, you can just peel them off because graphene provide a slippery surface. Then you can do the same thing for the different types of materials in different places. Then you can stack them up into one place. At the same time, you are able to produce ultra thin device layer, which is freestanding, free from the substrate. That way, you can stack them up, you can bend it, so you can have flexibility and the stackability. At the same time, you don't sacrifice the performance because it's perfect single crystalline. Also, we found the way to reuse this single substrate to produce many of these freestanding layers, so then we can also reduce the cost of single crystalline freestanding membrane. So we are able to produce cheap, flexible, stackable single crystalline elongated membranes. By having this capability, by growing perfect single crystalline material on graphene, by peeling off entire films from the substrate, by stacking this up, we can really revolutionize the future electronics. So ever since 2017, right after we put this technique in Nature 2017, we expand the material system that can be in the form of the freestanding materials. So 2017 we are able to do it for the 3,5 materials. 2018 we are able to do this for the all possible 3-nitride materials, and 2020 we are able to do this for the all complex functional oxide. So again, by growing graphene on 3-5 materials or compound materials, we are able to grow perfect single material. Then we peel off the entire film from the substrate. We are able to keep replicating this structure by reusing the single substrate. You are looking at the same clone of single crystalline gallium arsenide membrane, which is flexible and stackable, by reusing the single substrate. Okay. Also, we further reduce the cost of producing the freestanding membrane by inventing the multiplication method. the way it works is as following. We have the compound materials, compound material substrate, and we grow 2D material, monolayer 2D material in the MOCVD chamber. We grow, compound material, we grow 2D material, we grow 3D compound material, we alterate 2D material, 3D material, many times with a cycle. Then by performing only one single event of the epitaxial growth, we are able to produce this stack, and we are able to harvest the single crystal material from the top one by one, as you can see here. That way, you can really reduce the cost of this kind of expensive, single crystalline, materials. All right. So what is implication? Again, this kind of technique, again, two-dimensional material-based layer transfer process, 2DLT, I abbreviate it as a 2DLT. What is the benefit of 2DLT, 2D material-based layer transfer process? This is going to be a very strong tool for future electronics, again, because you can produce the freestanding stackable membrane with a cheaper price, and all existing single crystal material is now flexible, not in the form of the thick wafer, and you can stack this kind of single crystal material in one place. Again, previously, in order for you to stack this kind of single crystalline materials in one place, you are supposed to perform the heteroepitaxy, but heteroepitaxy is only possible for the similar material system. This kind of totally completely different material system, you cannot do the heteroepitaxy. Only way that you can do is just a step, to do the remote epitaxy and do the 2DLT to stack them out. So this really opened up the future of electronics. A lot of opportunity will be opened up. All right. So here's some examples of the implication and impact of 2DLT. How can we address the existing problem in current electronics? How can we open up the new opportunity? Here is examples. Okay, so right now, from now, my group can stack any kinds of materials we want. Okay, here's one example. All right, so we can again produce ultra thin freestanding membranes. Okay, the very popular electric materials in the market is gallium nitride. Gallium nitride, wide bandgap gallium nitride material is emerging semiconductor material for the future. Again, most of gallium nitride material is in the form of rigid wafer. Now, again, we can produce world thinnest, flexible, single crystalline gallium nitride freestanding membranes. Here's the impact. You can stack this kind of single crystalline electronic component on your skin. Here's an example. We produce only 200 nanometer gallium nitride membranes, then we are able to stack these gallium nitride membranes on human skin, electronic skin. Because this gallium nitride is ultra thin and flexible, is conformed on the skin, then by having it on the body, by having this electronic system on the body, we are able to monitor the light exposure, UV exposure. Okay, on the surface of the skin, but this sensitivity cannot compare to the sensitivity of previously used organic sensing materials, because this inorganic material. This is just a very straightforward example of utilizing single crystalline gallium nitride wide bandgap membranes. But this thing is not something that we can easily imagine. Please have a look at this. By repurposing this freestanding gallium nitride membrane for the sensing application, we are able to we are able to produce the chipless, batteryless, wireless bioelectronic system. Okay, so far, it has been well known that you can produce this kind of electronic skin where you can put the electronic component on the skin patch, and this skin patch interface between the electronics and the human skin. All right. So far, you can have a very light, electronic component on the body. All right. But in order for you to have the, for you to collect information from the body, you really need to have this kind of very bulky, chips, wireless, wireless NFC or RFID chips. So then you can have collect the physiological information from the body, and you can send the signal to the computer or your cell phone. So this kind of bulky chip is must to produce this kind of e-skin to collect information. However, this bulky chip cannot make a good interface with the body. So even if your e-skin, electronic skin can be conformal to the human body, but this chip is not. So for that sense, we actually repurpose this gallium nitride surface, gallium nitride materials. Repurpose gallium nitride materials for wireless e-skin. Please have a look at this. Okay, so we actually produced gallium nitride surface acoustic wave device on the skin. Okay, and once you form the gallium nitride based surface acoustic wave on the skin, then this SAW, gallium nitride surface acoustic SAW device will have the resonant frequency patterns. Once there's any change in the physiological activities, this resonant frequency pattern can be changed, and this resonant frequency can be detected outside by simply putting the antenna near this SAW sensors on the body. So this SAW GaN sensor on the skin now became the sensor as well as wireless communicator. So we are able to demonstrate really the chipless wireless system, as you can see here. Okay, let's have a look at this. By putting this GaN SAW sensors on the skin, we are able to measure the human pulses. Again, no battery, no chips. We only need to have just antenna at the edge of the skin patch, and we can read outside without having any chips. At the same time, we can also sense the ions from the sweat. We can also sense the UV exposure to the skin, okay, without having any chips wirelessly. This is one just a good example how we can make an impact by having freestanding, stackable single crystal membranes. Okay, this really unlocks a way to produce a bioelectronic component, a wireless bioelectronic component that does not have any, but does not need any chips or battery. Right. The second example. We can actually stack the colors. Okay, by having ultra thin RGB, red, green, blue LED single crystal membranes, you can simply stack this up in one place. Okay, but the key here is you really need to prepare the ultra thin RGB materials at the single crystal form, then you can stack them up. By doing so, you're able to produce vertically stacked, full color micro LED. You are looking at for the first time demonstration in the world, showing the world's smallest full color vertically stacked micro LEDs. Okay, how can we have this? Simply by having, again, 2D process, 2D material-based layer transfer process, which ensure us to prepare ultra-thin single crystalline LED membranes, which is inorganic, single crystalline, freestanding, readily stackable. Then we produce RGB and stack. This is the cross-sectional TM image of our pixels, vertically stacked RGB pixels, as you can see from here. By doing so, we're able to produce the 5,000 PPI, 5K, which is already beyond the requirement PPI for the AI, AR, or VR application. First demonstration. How can you do that? Because of having the color stacking by 2D LT. This is another example of making impact by having this 2D LT technique. You can actually stack the function. As you can see here, we can have freestanding piezoelectric membranes and freestanding magnetostrictive membranes. So you can just simply stack them up in one place, single crystal material. These two different materials cannot be epitaxially grown. So you can have freestanding, magnetostrictive material, freestanding piezoelectric material, then you can stack them up, then we are able to maximize the magnetoelectric coupling. Okay, this is another example. There's also a very exciting example for the edge computing devices. Okay, please have a look at this. Previously, as I have shown you initially in my talk, edge computing device has a sensors, memory, and logic device to process the information. What's the challenge here? All these layers has to be fixed in one place. So each layer actually affecting each other. So there's a limited number of layers to be stacked. Also, once you fix these sensors and memories and logic, it cannot be reconfigured. Once you fix the sensors, then one sensing information. If you fix the logic, then it cannot be reduced. It cannot be enlarged. At the same time, so far it has been shown for this edge computing task with conventional von Neumann computing method, digital method. Okay, here we are able to produce freestanding sensing layer, freestanding optoelectronic layers, freestanding AI layers, so that we can stack in one place, so that we are able to produce the reconfigurable, restackable heterogeneous integration system. Please have a look at this. We actually stack the photodetector and LEDs in one place. Then we actually pattern it as arrays of the LED and photodetector. Then we can also produce AI, artificial intelligence processor at the edges. Then we actually drill the hole of the wafer from the back of the photodetector and LED arrays. Then what's going to happen is quite interesting. You have, for example, you have this kind of sensors on the back of the system. Then you don't have to fix the memory and the processor right next to each other. This photodetector and LED will become the communicator by doing the heterogeneous integration. Then you can have the stimulation at the photodetector, then it will go to the AI. Your AI will process information. The process information will be gone to LED. And this LED will generate the light and send the signal to the next layer of these reconfigurable chips. That way, you can stack unlimited amount of the sensors and the processors in one place. This is also an example of stackable electronics. Okay, so today I try to show you the very unique system, very unique a heterogeneous system that was enabled by having freestanding single-cell membranes. Okay, so what's the future? Because we know how to produce freestanding single crystalline devices. Obviously, so many things can be done. This is just a beginning. We are going to make an excellent interface with the human body by integrating the AI chips with the sensors on the body. So we're going to have a sensor fusion task with a wearable AI. We are going to have an excellent brain electric interface. We're going to have also light therapy system with single optoelectronic system. Also, we're going to have implantable electronics because we can have a magnetoelectric coupling device which is freestanding. Okay, so this is the end of my talk. And thanks to all of my group members here working hard to realize this concept, we are able to produce, almost unlimited, spectrum of freestanding single-cell materials and totally different types of, heterogeneous integration system. Thank you so much for your attention.